Yeah, then I would say let's get started. So hi everyone and welcome to the second meetup on the modern data stack. So we'll have two speakers today. One is myself. Sorry? Yeah. So, okay. Yeah, one is myself. So I will give you an overview of testing database systems with SQLancer. Then I think we'll have a short break, right?
Yeah, Q&A session.
Mm-hmm. And then Zhi LIU Martin here will present the second talk on RisingWave. Good. So yeah, so my name is Manuel Rigger. I'm a tenure-track professor at NUS, and I'm leading the Trustworthy Engineering of Software Technologies Lab, or short TEST Lab, which I recently established. And one of our research focuses is that actually we have all these different kind of data-centric systems out there. So systems that take data as an input, that process it, store it, and so on. And we want to provide some confidence that the systems work correctly so that they are reliable in terms of different aspects, for example, correctness, performance, security, and so on. So this is our lab's research vision. And in this talk, I will focus on a very small domain. If we actually compare it to the landscape of data-centric systems, of AI systems and machine learning ones. So this is actually an overview that was designed, a landscape overview that was designed by Matt Turk to illustrate this landscape of data-centric machine learning and AI systems. And in this talk, as mentioned, I focus on this very small, I'm not sure if you can see it here on the screen, but there is a small red rectangle over relational database systems. Specifically in this talk, I'm going to tell you about SQLancer, which is a system that I designed and developed, which implements new techniques for testing database systems. As you can see, SQLancer is available on GitHub, so everything is open source. There's also a community around it with a Slack workspace and so on. So if you're interested, feel free to ask any questions, try out the tool, and if you even want, you can, of course, contribute. So just to ensure that we're all on the same page, in this project, we primarily considered relational database management systems. So those that expect statements written in the structured query language or short SQL as an input. For example, as I guess most of you know, using this language, we can, for example, create a table, we can insert some data into it, and then we can use a select statement, a query, we can fetch our data. So how can we now test such relational database systems? And I guess the most straightforward way is that we write unit tests, right? So here, for example, we can see a unit test that was written to test MySQL. And you can see that first we write the SQL statements, which are part of the test case. And then the other part is the result that we actually expect. And you can see here that in addition to the statements down there, the expected output is included in this result file. So this, of course, works well. It also likely allows us to find some bugs and prevent some regressions from being introduced. But I would say that it's always challenging and time-consuming to write test cases, especially good test cases for such large software systems. So can we do better? And specifically, can we automate this testing process, at least to some degree? Well, if we want to do this, we need to look at two challenges. First is that we need an effective test case. And in our case, this might be, for example, a database that we need, some kind of state, and then the query that we want to validate. And there, actually, if you look what's already out there, then one of the approaches and tools, which is very popular, it's also highly effective, is SQLsmith. So SQLsmith is a tool that randomly generates queries, which are potentially highly complex. It sends them to the database management system and then tries to crash it to cause a segmentation fault. So basically, for the purposes of this talk, I would say we already have a feasible approach that we can apply to randomly generate databases and queries using a similar approach, such as the one implemented in SQLsmith. What about the second part of the problem? So we are also interested in validating whether the query produces the correct result or not. And this refers to the so-called test oracle problem. What's a test oracle? A test oracle is the mechanism that tells us whether a test has passed or failed. And in the case of unit tests, we are the test oracle, right? We write down the specification, what the expected output is for the respective input. But here we're interested in test oracles that we can use in an automated setting, so without actually having a user-specified expected result. Coming up with such a test oracle is difficult, even for manually written test cases. And I want to illustrate this based on an example. So you can see here a bug-inducing test case for MySQL. You can basically see that we already created two tables, namely T0 and T1. Each of those tables holds a floating point value, namely 0 and -0. And then we ask MySQL to fetch the cross product of all values from these two tables, T0 and T1, where the column averages to the same value. Now, what's the expected output here? Well, first of all, I would argue it's disputable whether the predicate should evaluate to true or not. Anyone wants to guess or comment why? You say true?
Yeah.
Why?
0.
Right. I mean, it makes sense. Let us first go to the second case here. So like you said, it should evaluate to true, right? Because this is the semantics that most programming languages provide, such as C and Java.
Yeah.
But actually, I would argue it's also plausible that it might evaluate to false because the binary representation is different, right? It's in one case, we have a 0 sign bit, and in another, we have a 1 sign bit. So I think that some people might still argue that the predicate should evaluate to false, and thus no row should be fetched. So I think you really need to have some domain knowledge in order to decide this here. Now, when we tested the latest version of MySQL, it produced a result that was wrong. And the MySQL developers fixed it for the next release of MySQL. But the point is actually, when we reported the bug, we didn't know whether the predicate should evaluate to true or false. We basically had this automated test oracle that we could use that told us that the result was unexpected. And yeah, I guess I didn't mention it here. But the expected result was that a row should be fetched. So you are correct. Right. Before I continue, so if you have any questions or comments, we can also make this more interactive. So just feel free to shout out and comment. So this now one natural question is, of course, what is the state of the art in terms of test oracles? And there a couple of researchers proposed some new testing techniques, but I would actually say that the most effective one still goes back to more than 20 years ago, where Microsoft Research proposed a system that is called REX. And REX implements two new ideas at this time, namely on how these queries are generated, actually quite similar to SQLsmith. And then as a second part, as a test oracle, this REX system uses what is nowadays known as differential testing. So what is differential testing? The idea is rather simple, namely that we have a random query generator that generates one query that is sent to multiple database systems. So I guess at this time, some of these database systems didn't exist yet, but the concept is still the same. And each of the systems then returns their own result set. And the idea is that we can compare whether the result sets are all the same or not. If they are the same, then everything seems to work correctly. If they differ, then at least one of the systems is affected by a bug. Right, so quite simple, but effective. Now, one problem that was already raised by the developer of REX is that actually this only works for the small set of common SQL. Well, why small? Because in practice, database vendors, they provide extensions to what is defined in the SQL standard, or they do not strictly adhere to it. So in practice, it's actually quite challenging to generate SQL statements that for which all the database systems are expected to produce the same result. So we came up with a different idea, or actually a couple of different ideas. And the first one that I want to present is called ternary logic partitioning, or short TLP. And the very basic idea of TLP is that we want to test the database system against itself. And the specific idea of TLP is based on a more general idea, a more general conceptual framework that we call query partitioning. So let me first explain query partitioning before I explain TLP in detail. And it's a bit abstract, but I hope you bear with me for a couple of seconds. So the idea is that we have a query generator that generates a so-called original query. You can also see here that this circle denotes the original query's result set. Then we derive so-called partitioning queries from this original query, each of which computes a so-called partition. And then the assumption is that we can come up with a composition operator that allows us to take this partition and combine it to a new result set. And the assumption is that we create the partitions and the composition operator in such a way that the original query's result and the composed result is the same. Now, if this is actually the case, then the database management system seems to work correctly. If not, then we have found a bug in the system. So that's the basic idea. And here, in contrast to differential testing, we now only need a single database management system, right? So we don't really need to care a lot about these different SQL dialects. But the key challenge here still remains, right? The idea was quite abstract. We still need a valid partitioning strategy that stresses the database management system in various ways. And before I explain how this approach works in the context of SQL, I actually first want to explain it based on an analogy. So I actually moved to Singapore from Europe about 1 month ago. And one thing that I've been showing a lot is dragon fruits, because they are hard to find in Europe. And if you find them, they're quite expensive. So as you can see, I eat them as is, or sometimes mix them, blend them together to make some smoothies or something. Now, one thing that I figured out is that I believe that the red dragon fruits, they are a bit tastier than the white ones. I think I read that actually they contain a bit more sugar. So, but anyway, they are tastier. But for me, it's still possible to tell them apart. So I don't really know what's the difference, how to distinguish red from white dragon fruits. And I guess many of you are very familiar with the difference. So you might just tell me, well, I should just look it up on the web. So the scales are different, the skin is different, flower margins are different, and so on. So based on this, I should be able to actually distinguish them. But I still don't buy this because I'm still unable to tell the difference between them. So how can I test your understanding if you actually know the difference or not? And the idea that I'm applying here is I would first ask you to bring me all the red dragon fruits, and you perhaps would go ahead and bring back 2 of them. Then I would put them back in a bowl, shuffle them around a bit, and then ask you to bring me all but the red dragon fruits. And again, you would go ahead and perhaps bring me back 4 of them. And perhaps you already noticed now that actually in the first round, you brought me 2 dragon fruits, in the second round 4. So over 6 fruits, but there are only 5 fruits in this bowl here, right? Meaning that you likely classified a dragon fruit as being both a red and a white one. And this basically allowed me now to test your understanding without even knowing myself the difference between red and white dragon fruits. So the insight here is that every object in the universe is either a red dragon fruit or not, right? I mean, this pizza here, for example, is not a red dragon fruit. And we can use this insight to also test the implementation of database systems. Namely, now we have any kind of random predicate phi. So we no longer check whether something is a red dragon fruit, but any kind of predicate and a given row R rather than a fruit in a bowl. Then exactly one of the following must hold. The predicate evaluates to true, the predicate evaluates to false, meaning that not the predicate evaluates to true. And now, since we're also dealing with SQL, where a Boolean predicate might also evaluate to null, we also have to account for this. So we have to test whether the predicate evaluates to null. And we call this the ternary predicate variance. Now, based on this, we can take any kind of data in our database, any kind of intermediate result, and partition it into 3 parts, namely those where the predicate evaluates to true, where it evaluates to false, and where it evaluates to null. Now, how did this allow us to detect the bug from the motivating example? Well, we first generated this original query that basically corresponds to just counting the number of fruits in the bowl. And here, MySQL returned a single row, which is expected. But then we derived this more complex partitioning queries based on this random predicate phi here, which compares the 2 columns. And you can see here that we have the non-negated version, the negated version, and the is null version of this predicate. And for this query, MySQL returned an empty result, which was unexpected because we constructed these 2 queries in such a way that both of them should compute the same result. And this is how we were able to find this bug without even having the understanding ourselves. So we didn't know exactly which of the queries should have fetched the result, or perhaps whether the query on the left is wrong or not. But we knew that something was wrong because the results should not mismatch. So why did this technique work in this case? It works because the database management system is more likely to process the partitioning queries incorrectly because they're more complex than the simple original query that we had here. And this idea is actually quite versatile. It can be used to test quite a variety of different SQL features. So now we saw basically an example for how we can test the implementation of work clauses. And as you saw in the example, we first had this original query, and then we derived this partitioning query with the 3 variants, with the 3 ternary predicate variants. And for the composition operator, if you paid attention, actually, I didn't explain it before, but we use this union all keyword, which filters out or which combines records without removing duplicate rows. So this is also known as the multi-set addition. Now, I also want to provide an example of how we can test another category of SQL functionality, which are aggregate functions, which compute the result over multiple rows. And there the idea is quite similar. So again, the original query and the partition query look like before, but now the composition operator is perhaps a bit more complicated in the sense that now a partition is an intermediate result, namely the maximum value computed over the respective set of rows, rather than a subset of the result set, which was the case for this were test oracle. This now means that we need to use the max aggregate function once again to compute the overall maximum value. To illustrate this based on a concrete example, so here is a bug-inducing test case that allowed us to find a bug in CockroachDB. And there we first generated this original query where we computed the maximum value of this row ID column, and CockroachDB returned a single row with a value null. And then we derived this more complex partitioning queries. And you can see that here we first have an inner application of the max aggregate function, which computes the maximum value over the respective set of rows. And then we need to apply the max function once again to compute the overall maximum value. And as you can see below here, CockroachDB returned a different result than from the first case. So this is why we were able to report this bug. Besides so-called self-decomposable aggregate functions, there is also another category of decomposable aggregate functions. So I directly explain it based on the example rather than trying to define the term. So if we actually think about testing the average function, then it quickly becomes clear that a single value to represent the partition is insufficient. Because if we would, for example, just take the average and compute it over some rows, at the end, in a composition operator, we wouldn't know over how many rows we computed it. So here what we do is we keep track both of the sum and the count in the partition to then be able to reconstruct the overall average. And similar insights can also be used to test other SQL features, for example, group bys, distinct clauses, and having clauses. So when we first described our approach in the paper, we evaluated the effectiveness on 7 widely used database management systems. So from this, you can already see it's actually quite easy to realize because I was able to implement this for 7 database systems. And in this period when we tested it, we were actually able to find and report close to 200 unique, previously unknown bugs. And after we reported these bugs, the majority of those had already been fixed or were fixed after we reported them. So I think now the percentage would even be higher than this. If we look at the test oracle that allowed us to find these bugs, then we can see that the word test oracle is not only the simplest one on a conceptual level, but also actually the most effective one. The other test oracles, they found interesting bugs, but fewer overall. And you perhaps also noticed that we actually also found a lot of crash bugs. Those could have been found by SQLsmith or other random query generation tools. And for error bugs, I just want to briefly explain. So there we checked for unexpected error messages. For example, you can see here a generator that generates insert statements for DuckDB by basically selecting a random table, selecting a subset of the columns, and then trying to insert values. So this is how we implemented the database generator here for DuckDB and for this specific keyword. And what you might notice here is that we add a list of errors. Why do we do this? Because it's actually quite easy to syntactically generate valid statements, but it's not that easy to do this to produce semantically correct ones. So it might be that, for example, here you can see in the first line that we violate a not null constraint, or we might violate a unique constraint. So rather than trying to prevent this, we just specify this as a list of unexpected errors. And the insight is that some errors, they're always unexpected. For example, for various database management systems, we got back an error that the database is corrupted, right? So you never want to get this error. If you do, then something went wrong. Now, I guess while I explained the technique, you were already thinking, actually, what if you consistently say it's a red dragon fruit, but actually it's a white one, or the other way around? Then TLB fails to detect such cases, right? But we're still fine with that because testing in general doesn't allow you to find all the bugs. You need to resort to formal verification also if you actually want to have some guarantees. And we're already happy if we find some of the bugs in the database system. Now, the technique that I presented primarily works for data-oriented systems, but it's actually based on a more general technique. So I also want to mention this. Namely, we had this original query that we executed and then obtained the result. So on an abstract level, we had this test case that we executed to then get the result. And based on this, we derived a new test case for which we could then provide the test oracle. And this technique is actually known as metamorphic testing. So it's a bit more general idea of how to test a system automatically. So ternary logic partitioning was the latest approach that we proposed to testing database management systems. It's a metamorphic testing technique, and one that we proposed before, non-optimizing reference engine construction, or short NOREC, is also a metamorphic testing idea. So the approaches actually differ quite a bit. For this one, the idea was that we specifically wanted to find optimization bugs by basically having a query that might be optimized by the database management system and then rewrite it to one that cannot be efficiently optimized. And by then checking their results, we could basically find bugs in the query optimizer. But yeah, since it's also a metamorphic testing idea, I will not explain it here. Rather, I will go actually to the next approach, namely pivoted query synthesis, or short PQS. And there the idea is that we implemented a divide and conquer approach, basically, based on the idea that we want to validate the database management system one randomly selected row at a time. So let's look into how this technique works. Basically, we tackled both the test case generation problem and also the test oracle problem. For the test case generation problem, we basically generated a meaningful test case, meaningful in the sense that at least one row will be fetched by the query. And then for validating the result, we checked that this pivot row that we randomly selected is indeed fetched. And this technique now is a bit different than NOREC and TLB. It's not a metamorphic testing approach. So in contrast to the other ones, it provides some ground truth. But the implementation effort and the effort in general to realize it is a bit higher. Because pivotal query synthesis uses some expression evaluators to provide a ground truth, and these need to be implemented by someone who is testing the system. Well, so how does the technique work now? I want to illustrate this based on a bug-inducing test case that allowed us to find a bug in SQLite. Here at the test case, one thing that I want to note is that this is not operator, is a null-safe comparison operator. So no matter if the operand evaluates to null or to some other value, the operator will always return either true or false. Now, what's the expected result here? Well, 0 is not 1 should evaluate to true, so this should be part of the result set. 1 is not 1 should evaluate to false, so this will not be contained. 2 is not 1 evaluates to true. And now, since we are using this null-safe comparison operator, null is not 1 should also evaluate to true, so this should also be part of the result set. Now, when we tested the latest version of SQLite at that time, it failed to fetch the null value. And the technique that I'm going to present now was able to find this bug. So the idea is as follows. In the first step, we select this pivot row, which is conceptually only a single row, but it might actually stem from multiple tables and views. Then as a second step, we need to generate a query that indeed fetches the pivot row. So we don't really care about any of the other rows in the database. We want to simplify the problem by only considering one row at a time. And there the insight is that we only need to generate predicates that evaluate the true for the pivot row. And then we can use them in any kind of join clause, for example, also left join, right join, and so on, and in where clauses, knowing that the pivot row should be part of the result set. Now, let's first assume that we generate one random predicate, namely the one that actually triggers the bug from before. And as I mentioned, we implemented an expression evaluator for every of these nodes. How do these nodes or these executable nodes work? Well, first of all, they consider only the pivot row values. Meaning that, for example, now if we have a column reference, such as here the left child node, then it returns the value from the pivot row. So we don't need to care about any of the access methods, for example. When executing this, we just take the value from the pivot row, which is null here. Then the other kind of leaf nodes are constant nodes. So they return their assigned literal values. And then compound nodes, they compute the result based on their children. So here, this node that we implement needs to check that null is not equals to 1. And this returns true. Now we know that the predicate is true, so we can directly use it in a where clause. We could have also used it in a join clause. Well, what if the expression does not evaluate to true? One simple approach to fix this is to have an additional check. So if it, for example, evaluates to false, then we'll append this not operator. If it evaluates to null, then we also add this is null operator. Alternatively, you could also have checked that the pivot row is expectedly not fetched if the predicate evaluates to true, but this would make things also a bit more tricky with, for example, join clauses. And as a final step, we rely on the database system to check whether the row is indeed contained in the result set. For example, for SQLite, we use the intersect operator, and then if the result is non-empty, then the pivot row is contained. So this was actually the first approach that we designed and implemented. At this time, we only evaluated 3 database systems, but as you can see, the technique was highly effective. So it found quite a number of bugs in mature database systems. So I hope at this time of the talk, you're already quite excited about trying SQLancer. It's actually quite easy to run it. So you can basically clone it from GitHub. It's written in Java and uses Maven, so you can use Maven package to build it. And then if you're interested in quickly trying it out, then I would suggest that you use an embedded database system, because there actually the database system is already contained in the database driver. So you don't need to set up any external kind of database system. SQLancer has also been widely adopted by companies. So this slide is actually quite outdated. There are now many more database systems that use SQLancer, but I still want to illustrate this. So for example, DuckDB, they run SQLancer and TLB on every pull request. Then Yandex, they contributed a TLB implementation to SQLancer. So actually also other companies, for example, and Finance, they contributed implementation for OceanBase. And ClickHouse also runs this regularly in their CI tests. Then MongoDB Solutions, they published a blog post a while ago. They still have been actively using SQLancer. So they, I guess, found now much more than 100 issues. PinkCat, they implemented their own implementation of SQLancer, because I think the idea is quite simple, right? So also, for example, Cockroach Labs, they pair TLB with their own database and query generator. Yeah, and as a final example, Cytos, which was acquired by Microsoft, they also had an intern working on this, and she also did an excellent job implementing this, and she also explained her experience in this blog post here. Yeah, with that, I want to summarize what I've presented. So at the beginning, I started by basically showing you these manually written test cases, which is, of course, reasonably to do, but it's time intensive. It requires domain knowledge, so it's quite tedious. And here is one alternative to at least complement manual testing. I propose that we can couple a random test case generation approach with test oracles such as TLB or PQS, which then effectively allows us to find and prevent many bugs. Yeah, so with that, thanks for listening, and looking forward to your questions and comments. So if you have no questions, any other ideas on how we could actually come up with additional partitioning strategies? I think that's also an interesting problem to look into. Or perhaps a different question. So is it surprising to you that actually TLB and so on are that effective, because the technique is quite simple, right? The systems that we tested, they're also very mature. So for example, SQLite has been developed for more than 20 years, I think. And they also have an extremely impressive testing process, yeah. Right. So they achieve 100% MCDC coverage, which is a very strict coverage metric.
So I'm really surprised. Like, still, the bugs can be fine.
Yeah, and we're not finished yet. So actually, one student that I've been working with here has also developed a new approach for bug finding. So Qinsheng, and he actually found more than 50 additional bugs now in a couple of database systems. So I think it's an exciting direction where there's actually still a lot to do and to achieve.
By a different strategy.
A different strategy, right.
So nothing to do with partitioning.
Right, it's a separate one. So in RisingWave, are you already using SQLsmith, or?
We integrate our own version of SQLsmith. So also quite some bugs. Some motion is not implemented correctly.
Oh, I see.
So,
but do you also have a way to tackle the test oracle problem to validate the results, or you're just looking for crash bugs at the moment?
Just looking for crash bugs at the moment. Usually we want to find multiple bugs. So RisingWave has like two ways of processing. One is batch processing, and the other way is stream processing. So we can just compare the results of the batch processing with the results of stream processing to see whether there's any difference. If there is one, that would be fine.
Interesting. Okay, so that's, I guess, an application of differential testing on a conceptual level.
Yes.
Do you have any questions from the online audience?
So I actually didn't check.
Or maybe I can ask a question, like a general question. So, like, what do you think are some like valuable like future directions or future works in this area like of database testing? There's no mention about partitioning, and so is it like one general direction is how to come up with more strategies to test the database?
That's a good question. Like it's difficult to say. I think, like I guess my perspective on this is that it's useful to create a toolbox of different tools that developers can actually use to make their systems better, to basically tackle this issue from various directions. So I think like one complementary kind of direction is, for example, isolation level testing, right? There is this Jepson framework, which is very widely used. And this framework developed by Caius Kingsbury, like he's trying to find specifically isolation kind of level bugs and bugs in distributed systems. So I think that's a great approach and an idea to tackle this correctness problem from a different direction. I think one direction that is interesting is also to come up with new approaches for finding missed optimizations or performance bugs in database systems. So I tried to come up with approaches to tackle it, but it's quite tricky to do this. Or here, like I demonstrated that we used a quite naive approach to generating databases and queries. So can we be smart about this and, for example, give some kind of guarantees, some kind of confidence that we actually, for example, if you use SQLancer, that we can use it to prevent regressions from creeping into a system. So I think there are a lot of different smaller, or not smaller, but different directions that it would make sense to look into.
Thank you.
Okay, thanks. Yeah, I guess, so there is a comment in the chat. Let me just check. So I think we can actually just go into the break, right, and enjoy the free pizza. Okay. So haha to all the virtual attendees, you don't get the pizza here. Please join the next time. Okay.
Thank you.
Thanks.
Okay, so in this talk, I will talk about, what RisingWave is, right? So RisingWave is a distributed SQL streaming database designed for the cloud. And I think I will just try to explain what streaming database is and what does it mean by designing for the cloud. So before stream processing, we have this kind of batch processing thing, right? So a typical processing pattern is that we accumulate data for a long time, maybe hours or days, and then we do the processing for all the data that we accumulated during this period of time, right? The problem is that if, let's say, we want to know the query results frequently, like once the new data comes in, we want to know the updated query result. This batch processing method is not going to deliver the results in very low latency. So then we have this kind of a stream processing, meaning that we are always ingest data into the system, and then we process it, and then reflect the changes of the data, or let's say changes of the state into the query result, right? So by doing so, we can have really fresh result, let's say at the second level latency. Right. So the reason we want to use stream processing is because by having the latest insight, we can make more accurate decision, right? So by making more accurate decision, we have more business value extracted from the data we have, right? But another problem is that doing stream processing is normally very costly because you keep the system running, right? And you would also need to keep the if you are doing some stateful jobs, right? For example, you're doing some aggregation in a streaming job, you need to keep the state in your system. So basically, you need to store possibly a huge size of data, no matter in memory or in disk. That incurs a lot of cost, right? So for RisingWave, one of the objectives is that we want to bring the cost of the stream processing down. Right. And this is like the major motivation why we design the system. Stream processing is not really a very new idea. As we can see, the first idea of stream processing come up at almost like 30 years ago, right? I think one of the problem of these like previous generation system is that let's say the first generation system is that they don't really have a lot of target use cases because, you know, like before 21st century, we do not really have a lot of stream data. We do not even have a lot of, let's say, static data, right? So we just use some RDBMS and it's enough for almost all of the use cases, right? So in the past decades, I think people get more and more interested into stream data because we just getting, like every company, every internet company is getting more and more data at every second. So streaming processing is not only bring a lot of value, sometimes it's the only way you can handle such a large volume of data, right? So now we enter the cloud era. Basically, it means that we can have a lot of different kinds of resources and even unlimited resources from the cloud vendor. So it may be a good opportunity, or let's say a good time for us to like revisit design and come up with a new design to handle like the like in this new hardware setting, right? So in the previous generation, like the big data era, people have already invented a lot of systems, right? So for example, most notable one would be Apache Storm and Spark Streaming and Apache Flink, right? But the problem is that they are really designed for the previous generation setting, meaning that a lot of companies using their own, let's say, cluster, right? They buy a lot of machines and they assemble a private cluster, and then they just deploy all kinds of system into that cluster. So this is the how people do things in the big data way. The philosophy of big data system is like, you first of all have this kind of MapReduce style processing, right? So you just kind of declare the job in some map operator, in some reduce operator, and even some, let's say, join operator. The problem this thing is that MapReduce is not really a very effective way of processing, right? So it just kind of utilize the resources in a brute force manner. It does not really have any indices. It just kind of loaded the data and try to process it into an embarrassingly parallel way, meaning that you can just distribute the job onto many number of machines, right? So this is really just brute force way of processing, so it incurs very high performance cost. And second is that it exposes only like low-level APIs, right? So to learn this system, people have to go through its API doc, and also by writing these low-level APIs, people often miss the opportunity of doing optimization, right? So you have both high development cost, and also you always like stuck with the suboptimal performance. And the third is that in the big data era, people have this kind of a Hadoop-based ecosystem, right? So you may need some, let's say you need a file system, a distributed file system to persist the data, right? To do the checkpoints. And you also need to use Yarn, this like cluster management system to deploy your jobs and manage the life cycle of your jobs. The problem is that when you try to deploy, let's say, a stream processing system, you also need to deploy a lot of other stuff together with it, so that the stream system can eventually be really used, right? So this kind of always gives a lot of trouble for people to actually, really get started with using the system. So the idea of RisingWave is that we try to build a cloud-native stream database to solve all the three problems that we mentioned in the previous slides. Right. So the streaming part, meaning that we just want to process data that constantly ingest into the system at a low latency. For the database part, it means that we want to manage the storage by ourselves, right? And we also not only just let's say doing stream processing, we also want to provide those serving queries, meaning that those ad hoc queries you can query against the view, or let's say the state, constantly updated by the streaming queries. Yeah. So basically, we want to provide a database interface for streaming processing, right? So we want to use this RisingWave just like we use like Postgres, use SQLite, just like MySQL. So this is the, let's say, a classic example of, let's say, a pipeline in a company, right? So we have the source data, we have some event data, we also may have some streaming CDC. CDC means that we are trying to capture the data changes from a OLTP database, meaning that when people do some transaction, they just log out all the changes that transaction made to the database, and then we just process these changes to our downstream application. And then the second stage is that we have a streaming engine there, no matter it's a Flink, Storm, or Samza, and then we will output the results to let's say a serving system, right? No matter it's a key value store or an OLTP database or a OLAP database. So this serving system is for the downstream application to query, right? So we can have some reporting application, monitoring application, alerting application. They just issue like, if it's a key value store, you just issue like get by key, or if it's an OLAP DB, you just issue like normal SQL queries to, let's say, serve your application logic. The idea of RisingWave is that we want to replace the second stage and the third stage, right? So if we can successfully do it, no matter for the upstream or the downstream, they can just treat RisingWave as a normal database, right? So we don't need to like deploy multiple systems to achieve the same goal. And for the cloud native part is because nowadays cloud vendors offer various different kind of resources, and we can utilize these resources differently when different from the way we use resources in the big data era. And I will explain this in the details later. One of the key differences between big data and the cloud era is that in a big data era, people usually just buy a lot of hardware and then they just assemble let's say a fixed cluster, right? So the resources is kind of fixed. So what people want to do is just kind of squeeze all the performance out of these fixed amount of resources, right? So in cloud era, we have really like unlimited resources we can have from the cloud vendors, right? So we can use high performance resources, right, for those high performance applications. So it really comes down to the question is that how can we minimize the cost to serve different kind of application which have different kind of a cost performance trade-offs. So one of the thing we can do in this cloud era is that we want to build a decoupled compute and storage architecture. So by doing so, we can scale the computation and the storage in independent way, right? So if we have more computation to do, we just buy more CPU. If we have more data to or intermediate result to store in memory or on disk, we just buy more disk. We no longer have a fixed cluster. We can always kind of increase the resources we want. The second point is that we want to offer a database interface, right? SQL is still very popular. I think a lot of database trying to replace SQL with some other language, but they always fail, and people return to SQL for their application development, right? So SQL is really popular, so we have really like lower learning curve, so we have low development cost, and by building like a cost-based query optimizer inside the database, we just free the application developer from manually optimizing their query by themselves, right? So we can have like better performance. And third is that we want the user to like use our product easily. So they don't need to manually deploy the system with a lot of other components. They can just use our database, and we manage all the other components by the database itself. Right, so in this way, the user you know, can use our system just like they use like Postgres or MySQL. So the stream processing job inside RisingWave is expressed as materialized views, right? So here we declare a table. You can consider the table as a source. It can be a Kafka source. It can be some kind of other database upstream as the source. And then we try to create a materialized view, right? So we keep absorbing the input data from the table T1. And in this case, we are maintaining a aggregation, aka the sum, right? And then as long as we keep like insert values into the table one, the results will be constantly updated in this MV1, this materialized view, right? And for the downstream application, if they want to know the latest result, they can just issue a select query from this materialized view. So as you can see, we kind of, people just need to use SQL, right? So this is the standard way of, let's say, using RisingWave. A lot of the jobs in stream processing require a state management, right? Because if we want to do aggregation, we want to do join, if we want to do window, these operators all need to manage the state. And the state management is a key topic in stream processing because first of all is that we need to make it efficient, and also we want to make it fault tolerant, because stream processing is long living queries. We cannot afford losing, let's say, or cropped the data. Right. So consider this example. We have two input stream. One input stream is impression stream, and the other one is click stream. This is a classic example in advertisement application, right? So in this example, we are doing a drawing on these two input streams, and we are doing drawing on the ad ID, right? So we would have a hash table for both of the input stream because we are doing hash drawing, right? So if, let's say, we have a lot of data come into the system, we may want to scale our computation power, right? But the problem is that in a big data era, node is like the minimum resource unit, right? So if you want to scale the computation, you kind of always scale the number of the machines. So you are kind of scale both the computation and the storage resources, even when you just want to scale the computation resources. So in this case, what we do is that you can, as we can see from the picture, we just add 2 more nodes into the job, and their nodes bring additional computation resources and additional storage resources. The problem of doing so is that, first of all, when you add more nodes into the job, you need to migrate the state, right? So if we are doing a hash join, we are basically partition this state by hash value, right? So if we add more nodes into the job, we need to reshuffle the state and repartition the state to all the new nodes, right? So this involves a very complicated and also time-consuming migration process. And the second is that even though we just want to scale out the computation resources, we are also scale out the storage resources, which is not necessary, right? So in this case, we have very low resource utilization on storage. Of course, I mean, if we want to scale out the storage resources, right? So in this case, we may have low resource utilization rate on computation resources. The root cause is that in this big data system, we are basically partition the state and make that state, make every partition of the state locally confined to a computation process, right? So only that computation thread in this process know that it is managing a partition of the state, right? So if we want to do the migration, it will be very complicated. And also, it's because like people haven't really figured out that state management is really the most important thing when you do stream processing. So they just use some off-the-shelf existing key value storage system as the state management backend. So they do not really design the state management as a first citizen in stream processing system. So the side effects would be that as we just mentioned, first of all, is that resources are not independently scalable, right? We are always scaled by the unit of a new node, right? Second is that we don't have a holistic view of the storage and state as a whole. Also, as just mentioned before, only the local computation thread is aware of the state it is managing. However, for the storage part, we also need to invest a lot of resources when we do stream processing, right? So if we do not have a holistic view of the storage and the state, we can have some interference, which may affect the performance. And also, we may also invest the resources into some, let's say, places that is not the bottleneck of the current job. Right, so we want to have a holistic view so we can schedule all the computation and the storage services, and we can like use the resources more efficiently. And third is that we want to make sure that the state is shareable by all the computation process so that we don't need to migrate the state. Right. So this is always a very big problem when people try to use these existing systems like Apache Flink. The scale out and scale in process is not efficient enough. So we come up with a state first design, although it sounds very fancy, but actually it just has some straightforward ideas, right? So the first of all is that we want to decouple the storage and the computation, right? So we want to independently scale the storage services, because one of the reasons is that as we manage more and more, let's say the data volume increased, it is very possible for us to manage a much larger state, right? So the state needs some really good elasticity. And then second, we want to have full control of the entire storage across different nodes. Again, we want to like invest the CPU resources in the job to computation and also to storage in a reasonable way, right? And we also want to manage the resources dynamically. By using a existing key value system, we cannot do so because the storage system is like a black box to the computation engine. And the third is that we want to make sure the state is visible to all the computation process, which is very beneficial for scaling in and out. Yeah, so most of the existing system would just use a general purpose key value store like RocksDB or LevelDB, right? So they basically use local threads for both computation and storage, right? And the disk space is fixed with respect to a machine. And the second is that we have no cooperation among inter-process store instance. And we also have no cooperation between the storage threads and also the stream processing threads, right? So we cannot really allocate the resources as we want. And the third is that normally if you use embedded key value store like RocksDB, the state is only accessible to the local process, right? Which is also the reason why it's bad. It's very bad for migration and scaling and scale out. So one of the key thing on cloud is that like blob storage like S3, right? So S3 is kind of a unlimited scalable file system provided by Amazon, right? So you can just use as you want. If you have more data, you just put more data onto the S3 and you do not need to do anything extra, right? And the second good thing about S3 is that it basically provides unlimited bandwidth, meaning that if you have a lot of clients want to fetching the data from S3 or writing the data to S3, you can just increase the number of the clients and you just get your bandwidth increased. And third is that it is really accessible to all of the all the process in your job because they can just locate a file by the file path, right? So it is visible to all. Yeah, so the first major thing is that we decompose the compute and the storage, right? So if we're running out of the compute, we just buy more compute instance and the storage can be scaled automatically. And not just S3, and we can also buy some other storage service like EBS, right? So it's like a SSD. We can just buy more SSD and attach to the compute instances. But the naive solution is that we just store all of our state on this remote cloud storage like S3. The problem is that every state access would become a remote access, which is very inefficient, right? So we need to go through the round trip of network. And also S3 is S3 because it's not really designed for low latency processing. It is more designed for bulk processing, like batch processing, right? So this is not feasible if we want the latency of a streaming job is at a millisecond level. And also S3 is charged on a per request basis. So if we store all the state on S3, every state access would be charged, which is definitely not cost efficient. So we introduce another level of storage into our system, which is EBS. EBS is like SSD. You can attach it to multiple EC2 instance. EC2 instance is basically the compute instance, right? So we can treat S3 as a persistent layer, right? So we do not expect that data will be lost on S3, but we would just use EC2 and EBS as a cache. So we can just, it's free for us to lose any data if our compute instance go down, or let's say EBS has some problems. And another good thing is that EBS is charged. You can provision EBS, and then you just can issue as many as requests to the let's say the disk as you want. It's not charged on a per request basis, so you can use this EBS layer as another level of cache when you try to access S3. Right, so in this case, we would try to keep all the hot data in the local memory of EC2 instance, and then we keep have the warm data in EBS, and we keep all the data in S3. So one of the difference between RisingWave and the existing system is that existing system, they would only treat S3 as a place they back up their files, right? But in RisingWave, we just like put all our data into S3 instead of writing data first into local disk, and then only at the checkpoint we move all the data from the disk to S3, right? So this is also, let's say, one point why RisingWave is cloud native. Another good thing about tier storage is that we can tune this trade-off between cost and performance, right? So for example, if it's a reporting application, most of the time minutes level latency is enough, right? So we can just use more of S3 instead of the local memory and the EBS, right? So if, let's say, it's an alerting application, we really want the results can be delivered at sub-second latency, then we probably need to keep everything in memory and the EBS, right? So we can just, according to the demand from the user, we can just use different amount of the resources, different amount of storage for their application with as low cost as possible. So our storage system is designed based on a data structure called log structure merge tree, right? So the reason why we choose this data structure is because the streaming workload is typically very write intensive, right? So for example, if you want to do a hash join, when you have the data, right? So for example, you do a group by aggregation, you have the key and you use the key to retrieve the value, and then you update the value, and then you write the value back to the storage system, right? So it's almost like the read and the write is 50%, right? And also when we do a hash join, we have to maintain the building table, right? So for the other side of the stream to probe, right? We also need to write every input records we have seen into the storage for probing later. And also because we maintain the materialized view, we will also need to update the materialized view frequently, right? This is the result set. So log structure merge tree is optimized for writes. The reason why it is optimized for writes is because there's a log structure in this data structure, right? So basically all the new writes will be put together and then do a append-only operation onto the, let's say, a file system or S3, right? So we don't have a lot of random writes. We always have sequential writes. By eliminating all the random writes, we would have very good write performance. And also, another reason is that people have been working on this data structure for a very long time, and there are a lot of production-ready implementation there, like RocksDB and the LevelDB, which is implemented by Facebook and Google, right? So people always take reference to this mature system when they try to build their own. Normally, like in, let's say, a lot of other databases, people would use B+tree as the storage engine, right? But LSM tree is normally, let's say, a default choice when you have write intensive workloads. Although, like, if you want to really do a very rigorous comparison between a B+tree and an LSM tree, you have to involve a lot of different factors. But the general conclusion is that, in most of the cases, LSM tree works very well for a lot of writes. Right? And also, by using cache and compaction is a very special operation in LSM tree, which is used to improve the read performance, right? So using cache and compaction to improve read performance is usually easier than designing a data structure which is both good for both read and writes, right? So this is also some, let's say, empirical reason why people always choose LS3 as the storage engine nowadays. Right. So, so this is a very simplified explanation for LSM3. So first of all, you can think that we can have a pure log structured storage, right? So every time we have some new key values into the system, we just append that new key value pairs to the end of the file, right? But the problem with this is that if we have, let's say, write a key value called the key is 1 and the value is 2, and after some time we write a key value pair with key equals to 2, key equals to 1, and the value equals to 3, then basically the first key value pair is stale, right? So we only need the latest key value pair for the state, for the key value access, right? So the problem is that if you do nothing and only do all the writes into this log structured storage engine, you will run out of the space, right? And also by keeping all the stale values in the storage, you will have very bad read performance, because every time you want to retrieve a key value pair, you may have to scan through a lot of stale key value pairs, and they are not really useful for the retrieval. Right? So the idea of LSM tree is that we keep a lot of different levels. For them, in this case, the C1, C2, and the CL is all kind of levels, right? So at first, we just try to write. So we first, when people use the API of the key value store, they just put the key value into in-memory data structure, right? And when we have enough number of key value pairs in memory, they will just be dumped onto the disk all at once into this C1 component, let's say, right? So if we decide, let's say, C1 has too many key value pairs, then we just try to merge C1 and C2, right? So basically, all the key value pairs on C1 is sorted, and all the key value pairs on C2 are also sorted. And then when we do this compaction, or let's say merge process, we just kind of do a merge sort, and then we try to eliminate all the duplicate values with the same key, right? So in this case, we can, in this compaction process, we can eliminate all the stale key value pairs, right? So normally the size of each component is bigger than the size of the previous component. I mean, the essence behind this process is that we do not really want to trigger too few compaction, right? So if we have too few compaction, we may still have a lot of still key value pairs in the system, which is still bad for the disk space, bad for the read performance. But also we do not really want to trigger too many compaction, right? Because when we do the compaction, we need to bring the files on the disk into memory, and then we do a merge sort, eliminate the duplicate ones, and then write the new file back to the disk. Right? So this is kind of a way for LSM3 to control the trade-off between doing many compaction or doing few compactions, to control like the trade-off between read performance or space amplification and the write performance. Right. So compaction is actually a very complicated thing, and a lot of academic papers have been published on this issue, right? So this is a very classic paper which discussed like how different compaction strategy can affect the performance of operation to the LSM tree, right? So for the read access, we typically would have like point lookup, short range lookup, and a long range lookup for streaming operators, right? So because we generally have a very fixed set of operators in a SQL-based system, right? So it's very nice if we can, customize our compaction strategy for different workload or even, let's say, different operator types, right? So for operators that issue point lookup only, we may want one specific compaction strategy. And for the rest, we may want to have a different compaction strategy, right? This is the reason why we want to build a storage system by ourselves instead of just using a general purpose one, because general purpose one would, it's always lead to a very suboptimal performance. Yeah. So this is basically the idea just mentioned, right? So we want to customize our compaction strategies and even frequencies for each job or even each operator type individually. As I just described, compaction can consume a lot of resources like disk bandwidth or network bandwidth when you bring the file into the memory. And when you do the merge sort in the memory, it's also very CPU intensive, right? So the problem is that the thread for compaction will compete with the thread for the normal computation for stream processing, right? So this is a very classic problem when people use a stream processing system in practice, because for the stream job, normally we want a very stable latency, but because this kind of interference, people would have very unstable latency because the compaction may be triggered periodically and unexpectedly, right? And the other thing is that we really want to compact for the bottleneck, right? We don't really want to waste this kind of precious CPU resources onto some operators whose performance does not really matter for the end-to-end latency of the entire job, right? So this is also what we can optimize by considering storage or, let's say, compaction for the whole job instead of just for a local computation instance. Yep. So if we don't have a holistic view, then we don't really have the co-scheduling opportunity of compaction and the normal stream processing, right? And this would lead to unstable latency. And normally people will try to tune some of the knobs to alleviate this interference problem. But the issue is that the general purpose key value system do not really expose knobs directly to this problem, right? People just kind of try to work around it. And also, even you have, let's say you find a very good configuration, but as the workload changes, you may stuck with a suboptimal one again. If we can only statically allocate the resources for compaction, let's say if we use existing key value store and we say we just want to use 2 threads for the compaction, the problem is that sometimes if, let's say, the workload is really intensive, then we may not have enough compaction, and the space amplification is getting worse and the read amplification is getting worse. So we just cannot guarantee a stable latency, right? And also, because there are different levels in LSM tree, and each level has a fixed size. If one level reaches its predefined size, basically we just cannot write any more data into that level. And normally we would have a write store problem. Basically, the writes become blocking, and it will affect the end-to-end latency also. Yep. So this is the problem we may have when we have too few resources for compaction. But if we have too many resources reserved for compaction, then we may just leave insufficient resources for stream processing, right? And also, if let's say there is not much demand for compaction, and these threads would just left idle, and this is basically wasting the resources. The key insights we have is that, first of all, streaming jobs normally provision more resources than it needs, right? So to handle sudden load spike, sometimes we just have really a huge amount of data coming to the system because, let's say, you hold some event on your website, right? So we normally would have more resources than it really needs during normal times. So we can use these kind of over-reserve the resources for the compaction, right? So we can trigger opportunistic local compaction on computation instance to utilize these unused resources. Another one is that compaction is basically stateless, right? So we just like pull in multiple jobs and do the merge sort and write the new file into the storage again. Even let's say the compaction fails, it does not really trigger a serious problem because we can just bring the files again into the system and do the compaction again, right? So it's a stateless task. We can simply, trigger a second run to accomplish the job. So the good thing about this is that we can use some serverless function provided by the cloud vendors to do this, right? So basically, Amazon has some Lambda function. Lambda function is basically you can trigger as you want, anytime as you want. But the problem is that Amazon would only reserve the function for like 2 minutes or 5 minutes, and then it has the chance of being taken back by Amazon, right? But the good thing is that we can trigger a lot of Lambda function because Lambda function is cheap, right? And also you don't really have a limitation on the number of Lambda function instances you can trigger. So we can, if let's say we have a lot of demand from compaction, we can just suddenly trigger a lot of serverless function to do the compaction, right? So basically, compared to the local compaction on the previous slides, here we do remote compaction. So therefore, we have a hybrid solution, right? So first of all, we trigger local compaction when there are idle resources in local computation instance. And then if, let's say, the stream processing need more resources, then we just preempt these local compactions. And we move these local compaction to remote compaction services, right? So, and this remote compaction services is really easy to be scaled. You can just, trigger as many services as you want. And the problem is that by doing local compaction, after you've done the compaction, you can just use the newly compacted files on your local machine. But the problem of remote compaction is that you need to prefetch a newly compacted file back to the computation instance. So there is some extra network overhead here. Right. And by building our own storage system, we can have let's say, an overview, a holistic view of all the operators for the job, right? So we can kind of decide whether we want to trigger a local compaction or remote compaction, or decide which operations state are urgent to be compacted, right? So we can all do the analysis in a centralized coordinator, right? So we only want to invest these resources for compaction on performance bottleneck. Yep. So this is the tiered storage part. Another problem for tier storage is that about caching, right? So what if we cache miss on EC2 or EBS? Fetching from S3 would incur huge latency for the upcoming input. Right? The way of alleviating this issue is that we can do out of order processing, right? So if let's say we have input record and we want to fetch its corresponding state from S3, and at the same time, we can just use this CPU resource for processing the next input record, right? At the same time, we are fetching from the S3. So we don't really have this head of the line blocking issue. But the problem is that we cannot really like randomly or reorder any two input record, right? Because there can be some kind of a dependency between input records. For example, if we the input record is the CDC stream from a OLTP database, right? So we may have some events like inserts, updates, and deletes, right? So for the same for the let's say same row of the same primary key, we can only do the insertion first, and then we can do the deletion, right? So we cannot really like reorder the events if they have the same primary key. Right. So so this out of processing is also constrained by some let's say application level dependency, right? But anyway, by doing this out of order processing, we can basically hide the latency of fetching from S3 by overlapping with some other processing at the same time. And the other good news is that in real-world stream workload, we have really strong temporal locality, right? So this is a newly published paper on Eurosys. So it runs some realistic workload on Apache Flink, and you find that a lot of operators have very strong temporal locality, meaning that if we have an RU cache, it should work very well, right? So recently accessed keys will be accessed again in the near future. So we can expect that there will be very few cache miss for processing real-world workloads. Yep. So this is for the caching. And there are some other performance optimization we can do, right? So like multi-query optimization. Because we are running streaming queries is running almost like forever, right? So if we can find some common subqueries between multiple queries, it could be very profitable, right? We just do not need to do the same computation, store the same intermediate result twice or even multiple times, right? And the second is that a lot of times application requires some very standard pre-processing of data, like they want to do some data cleaning, data transformation before they apply some business logic onto that data. So all of these jobs may share some common data cleaning, data transformation stage in the whole pipeline, right? So if we can share these common ones, I mean, there will be a lot of opportunities for us to share these common subqueries. And third is that normally when people trying to analyze some data, right? So people usually would analyze on a coarser granularity, right? So if they are sure that they are going to the right direction, and then they will apply the more finer granularity query to like get a more detailed insights, right? So so the pattern is that people build some query first, and then they just build more complicated queries on these existing queries gradually, right? So this is the reason why introducing multi-query optimization is very important as a database, right? So another thing is that we can customize our operator state layout, right? Just like mentioned before, the LSM tree has a lot of factors you can tune, right? So if, let's say, your operators have very different rewrite patterns, you should really customize for them individually, right? Because we have very not really many operator types in our system, because we support SQL, and SQL has a limited number of operators, right? So one of the strategy here is called SM tree vertical grouping. Basically, we just kind of in simpler words, basically we treat treat each operator as a separate LSM tree, right? It's an individual one. We can configure each individual LSM tree by different strategies: compaction strategy, indices strategy, and a caching strategy, right? So this is also something we are currently working on. So the final part is about the serving part, right? So previously what we are talking about is the streaming query part. So after the materialized view is being created and being maintained by the streaming query, a lot of downstream application want to query this materialized view, right? And these queries would be called serving queries. So the common practice is that people would write what we keep in materialized view into a separate downstream storage system, right? Like Redis, Cassandra, or other applications to query. But the problem is that it introduces an extra system, which is some extra operational overhead, right? And also, if, let's say, you really want to be have very high demand for the consistency and exactly one's delivery semantics, you may need to kind of intrusively modify the downstream storage system to achieve so. And typically, this kind of a stronger consistency across a different system would incur, let's say, larger latency because of the protocols and the atomic operations you introduced into this process. So RisingWave, since also offer this serving queries within the same database system, you don't really need to allocate another system, so less operational overhead. And RisingWave is intrinsically guaranteed for exactly one's processing semantics by the ABS algorithm, which mentioned in the last meetup, right? So right now, all the state and data is managed by the RisingWave, so we don't really have this kind of a cross system issues, right? So we can achieve consistency easily, and we do not introduce extra latency, right? And the third one is that our materialized view is also stored in this LSM tree data structure, right? So in LSM tree, we normally would have like multiple values for the same key, because some of the values may be stale, right? They are older values, but older values still can be queried, right? And older values is more likely to be compacted already. So if the compaction is already done, that means that when we query it, we just can scanning less data from the storage system, so we have better query latency. So this is sometimes very important, because some downstream application may want strict, let's say, 99 percentile latency to be bounded within a certain degree, right? So we can kind of trade off between freshness and the query latency. Another aspect is about failure recovery, right? So our majority of the data is maintained in S3, right? So in EBS and the local memory, we only use them as a cache, right? So by directly writing to S3 instead of only writing to S3 at the checkpoint time, we just don't really need to move files again from local disk to S3, right? So this is some overhead existing in, let's say, some current stream processing system. So no extra migration is needed. And for the minority of data on EC2 and the EBS, it's only for the caching purpose. So it's fine for us to lose them during system failure, right? So after we recover, we just do the normal stream processing, and they are just naturally populated back to the cache again. The other aspect is about elastic scaling, right? One of the advantage of RisingWave is that it can scale the system with theoretically zero downtime, right? The problem of existing system, as mentioned before, it needs to do a very complicated state migration process when they scale out, because you introduce some new nodes and you want the state reshuffled to all the older nodes and together with the new nodes, right? But since we store all our data on S3, so we don't really need to do this shuffling, right? So all the new nodes, they can just processing the stream normally, and they just go to S3 to fetch the data they want instead of migrating in advance, right? So the steps here is that we first do the checkpoint before scaling, right? We write to the S3, right? And the second step is optional because we don't really need to do the migration for cached states. And the third step is just we continue the processing, right? We just continue processing from the checkpoint we done in step 1. So this is also a very big advantage because stream workload is very naturally fluctuating, right? So if we can do this scale with very low latency, then we can just do scale this elastic scaling more often. And by doing this more often, we can waste fewer resources, right? So basically, that's it. If you have any question, you can join our RisingWave community, right? So ask any question you want to ask, and we will answer in more details there. Yeah, that's all.
There's one question about actually the last slide. So, is there any way where we can utilize, let's say, what the data source knows about the current workload? Also, for example, if a database system knows there is a lot of interaction going on, and then now a lot of data will be written and then sent to this change capture interface. Would it help to have some kind of advanced hints to the streaming database or no?
I see. So let's say when the database consumes the transaction, it has some updates, and it is aware that how many updates are being made. So it kind of notifies the stream system to scale out in advance. Right? I think, I mean, the time between the database system log out all the changes and the time when the stream system consumes these changes, the time difference is very small, right? So, yeah, maybe just like seconds. Yeah. So I think it can help, but maybe not that much.
Okay. So at the very beginning of the SQL example, I was a bit confused.
Okay.
We have this great table T1. But in reality, I guess there should be some kind of reference to some external data source, right?
Yes, yes. It can be all kinds of sources like the CDC stream from a OLAP database or a Kafka stream, where you read from a Kafka topic, right? So it can also be a table. So we just we can all consider this thing as a table. It's just an unbounded table, right?
And for this material, I feel like this will be incrementally updated.
Yes, it's always incrementally updated. So we only do the work that is proportional to the size of the data changes. Yeah.
And it also already works for window functions and this kind of things, or?
Yes, we have a window function like for example, tumbling window, tumbling window, hopping window. Yeah.
Okay.
That's cool. Mm-hmm.
About the holistic view of the data and state, I think it's quite. So can I just double confirm that? So this is actually achieved by having first like storing persistent, make the persistent storage using S3.
Yep.
And also by using the ES2 and EDS. Do you mind
okay.
more on the
yes. So I mean, this is kind of a let's say compared to using an existing general purpose key value system, right? So this system is like a black box, right? And for each, let's say, computation process, it will start an instance of this key value store system, right? And they are totally unaware of each other, right? So they just manage their files independently. They do the compaction independently, right? So it is very likely to they want to consume the resources at the same time and cause some interference, right? So if we build the storage system by ourselves, then we can manage the whole thing by ourselves, right? So we can decide when the compaction should happen, which state the compaction should happen on, right? And also by storing the system, storing the state onto S3. We just make it visible to all the computation process, right? They can just fetch the states they want, the key value pairs they want from S3 directly, instead of, let's say, we need to do a migration.
But that's, maybe I'm wrong, but because I believe maybe for Flink, they prefer local, as you mentioned, they prefer to have data stored in the local machines, and you then know to process that part of data. It's kind of like distributes the job to different machines, and they are trying to minimize the I think the data exchange or
data locality.
They're having the data localities. So here in this case, when we are using S3, we are actually will have more movements of data
across the network.
Yeah, across the network.
Yeah. So that's when the caching can help. Right. So it's like when you use Flink and the Flink use RocksDB. So all the data is managed by all the state is managed by the RocksDB, and the RocksDB use local disk to manage this. Right. And here for RisingWave, S3 is like the SSD for RocksDB, right? Yeah. So for the data locality, I mean, with the help of the caching, I think it makes very little difference. But by storing the state to S3, we just avoid the migration, the reshuffle repartition.
So I guess a more high-level question is, so in the past, I worked a lot on programming language implementation. And there in Java virtual machines and similar kind of virtual machines, garbage collection is of course a topic that people worked on a lot in the past. So I'm not so familiar with the LSM literature, but I guess the techniques are a bit related, right? On how we can contact or not.
If you are referring to the, let's say, the garbage collection of Java, right? So I guess it's more like you just work on all the references, right, and find those.
I guess also some tricks, like for example, that there is some kind of map, and then you can mark regions of updates or so. So it's, for example, there's some region-based kind of garbage collectors, so that not all of the heap is, for example, traversed. There's actually also some research about having different kind of memory systems, so faster, slower ones, or more reliable, less reliable ones. So I think you also have to tackle some similar kind of problems. Or
I think maybe it's a little bit different. So, for example, in LSM tree, you always write let's say a sorted array of key value pairs into the disk, right? So you have one array and the other array a newly written array, right? So if you have some new array coming into the disk, so some of the key values in the older version of the array may become useless because they get overwritten by the new key value pairs, right? So the way we eliminate these older ones, useless ones, is by doing a merge sort. Yeah. So like during this merge sort phase, we just know that which values we need to keep. We only keep the new value if we have two key value pairs with the same key. Yeah. So for the older ones, we just forget about it and only write the new ones back to this disk, right? So after the compaction, the two arrays being compacted will be marked as useless.
I see.
Yeah.
Okay.
Yeah.
So sounds a bit similar actually to copying kind of garbage collectors where there's
Yeah, maybe, yes.
But I guess I have to get familiar more with LSM stuff.
Okay.
So what are the next big plans in terms of features that you want to add to RisingWave, or in general the next kind of milestones?
I think there's a roadmap on the company website specifying all of these, right? I think right now the most urgent problem is for us to kind of make the system more stable, finding all the bugs. Yeah. So that's what we really care about at the current stage.
UDFs.
Yeah, user-defined functions is something I think we cannot avoid to support, right? What? Python?
Yes, I can put machine learning models inside.